Yeah.
And Bradley, tell me if I'm wrong, but I'm sure I evaluated this integral last semester. I must have.
I think you didn't.
Oh. Then that's
did
my
he?
mistake.
Maybe.
You know, this is a nice example because I do think it's a trigonometric integral. Not like the first two examples I gave you. By the way, I know I need to go back and do number 2. I'll come back in a minute. This is another trigonometric integral. I just think it's a very non-sophisticated one. Because I think using my reciprocal, I misspoke, my ratio identity, I think I can think of the tangent of x as merely this beast. Tell me if I'm skipping too much. If u is equal to cosine of x, just come into a u sub, not integration by parts. If u is equal to cosine of x, neglecting a numerical coefficient, is its derivative already a factor in the integral position? Yeah, because I think cosine of x's derivative is negative sine of x. And so I think I just simply get a negative 1 over u du, if I allow u to be cosine of x. But that merely gives me the negative natural log of the absolute value plus c. It's just that in back substituting, I think I've got to replace u with the cosine of x. Humor me. Tangent squared of x plus 1, just in trigonometry, tangent squared of x plus 1 is equal to secant squared of x. Derivative of tangent of x is secant squared of x. Derivative of secant of x is secant x tangent of x. I just rattled off 3 beautiful, intimate relationships between the tangent function and the secant function. Let me try to force the issue here. I didn't make any mistakes. But the integral involving tangent of x is expressed in terms of cosines. I don't like it. Can I think of this as a coefficient? Now, can I use my math D skills and bring that up into the exponential position within the log? And then rewrite 1 over cosine of x as secant of x? Only because, again, I like to have one more intimate relationship between tangent and secant. I just did. Makes sense. It was just a quick exercise.
Yeah, it's easy now that I think about it.
What do you think over here? I asked, what do you think over here?
Sine squared of theta squared.
I like it. What's another name for sine squared of x? A convenient name for sine squared of x.
One. Well, there's 2 things, but yeah, that's the best.
My reduction of order identity from trigonometry. And I think if I expand all this garbage, I get a 1/4 times the integral. I don't know. Is that a 1 minus 2 cosine 2x plus cosine squared 2x? You guys get quiet so well.
Yeah.
I want a yes or no answer. Piece of cake?
Yes.
Piece of cake?
Yes.
I think the only thing that's not a piece of cake is that last third term. So, if you guys don't mind, I got another name for it. It's merely 1 plus
Cosine of 2x
4x.
or 4x over 2.
But that is merely a 1/4 times the integral of 1. I misspoke. Is that 3/2? Minus 2 cosine 2x. Is it a plus 1/2 cosine 4x?
Why does that happen? Why does it become 1/2 cosine 4x from 1 plus cosine 4x over 2?
Here's why. So Reza, do you remember this one particular double angle identity for the cosine function? Just be honest. Do you remember this one?
I mean, kind of, but yes.
Okay, if you're going to say yes that fast, then check this out. I think replacing sine squared of x with this, just using my Pythagorean identity. And if I just remove terms, I misspoke, remove terms, remove parentheses, that can be this. Yeah, that's what I had on the board before. Now I want you to allow me to rewrite that. Oh, did I just erase that? Jeepers. If I take my x and replace it with, I don't know, any ideas? I am trying to come up with a different identity over there.
Huh?
All right, do
Why
this?
don't you just solve
Do
that?
this?
So
Just take this equation right here?
Yeah.
And just isolate the cosine of x? Well, I have to add 1 to both sides. I have to divide both sides by 2. And you guys, I fully understand back in trigonometry, you and I took the square root of both sides so we can get that thing we call the half angle identity, make that substitution, just not going that far. Notice how this is a nice convenient reduction formula, identity, that allows me to take cosine square root of x and replace it involving another expression involving cosine to the first power. The downside is that the input's more complex. The upside is that at least I've reduced my exponent. So Risa, check this out. If I had the cosine square root of 2x, am I just not going to replace x with twice that thing? I misspoke. Am I not going to replace this input with twice that input? I think it gives me this.
No, but I meant like from there to there, see how it becomes, then it just becomes 1/2 cosine 4x?
My apologies.
I know, I understood that.
I combined those to get that.
Oh, okay, so just,
I was being fancy with my words. My apologies for going through all that.
that's okay.
Do you guys think life's a piece of cake at this point?
Yes,
Can I stop?
if you want it.
Good. I was hoping to say that. Tell me what to do in words. In words.
Split up the sine 4 to the 4th power of x into 2 sine squared of x, sine squared of x. Now just apply your identities 10 times over.
That many times. You guys can stop writing. Yes, I'm sorry, sir.
Can you substitute sine 2x as a u and then take out your cosine?
Well, I don't have the sine squared of x, not sine 2x. I think that'd be different.
Yeah, I mean,
But if I allow you to be equal to
no,
sine...
I did now. I will.
You guys, no writing. If you allow me to imagine pulling out a factor of 1/8, I got 3 binomials multiplied to each other. What are you going to do next? What are you going to do next?
Foil?
Foil.
Foil everything out.
Yeah.
You're going to cut a constant term, piece of cake to anti-differentiate. You're going to get a cosine of 2x to the first power, coefficient out front, whatever that is. Piece of cake to anti-differentiate. You're going to get a cosine squared term. I misspoke. Cosine squared of 2x term. What are you going to do with that one term? Apply the reduction angle identity again. Along the way, however, you're going to get an integral. That looks like this. How are you going to deal with that integral?
Do the same thing, split it up.
I'm nervous. Oh, can we be small and split
Add
up?
another cosine of 2x. So cosine 2x.
And then I'll have to divide by it. Shoot, that looks nasty. What about shaving off one factor of cosine 2x? Think of this as stuff plus a constant times the integral of the cosine squared of 2x times the cosine of 2x with respect to x. Well, why is this going to help?
You're going to do the other one, or half equal, and then you put a cosine of squared.
Ooh, make me shiver, because now I've got sines and cosines of different inputs. It's complex. Okay, you're right. I've got cosines of 4x and cosine of 2x if I apply my reduction.
You could
Still the same problem.
you could just apply the identity to cosine squared of 2x
What
and
identity?
not 1 plus cosine of 4x over.
No, I think that's what you were just talking about.
I think, Bradley, that makes things complex, because I got cosine of 4x and cosine of 2x's. That looks kind of difficult to apply a use of to.
But well, yeah.
Wouldn't we want to do
Stop.
integration by parts?
But do you really have to do a u sub if you have cosine of 2x and cosine of 4x? Can't you just integrate that?
They're being multiplied together.
Oh, they're being multiplied together.
You guys stop thinking. I'm lazy. can't until I apply an identity, which is
Oh, you know what you could do? You could do 1 minus sine squared of 2x.
so equals stuff plus constant times the integral of 1 minus sine squared of 2x, use my Pythagorean identity, times the cosine of 2x with respect to x. You know what I'm integrating?
Now you could do u subs.
Basically a 1 minus u squared, piece of cake with a u sub. Do you see his point? So I think raising sine or cosine to even power, keep applying those reduction angle identities. If you're going to have a sine or cosine to an odd power, p sub k. You shave off one factor, repeatedly apply your Pythagorean identity, and it's going to be a piece of cake. Please don't see it. Can I do that again? Example 4. What about this one? What about the cosine to the 5th power of x with respect to x? What I just said, what's your approach, Dave?
I'm sorry, I just want to make sure I understand that properly. You would let your u be 1 minus sine squared of 2x?
No, just sine of 2x.
It makes things difficult. What about just letting u be equal to sine of 2x? Because that means du, neglecting a numerical coefficient, is already there as a factor in the Lagrange position.
I see, okay.
And that is why to transform as an integral,
1
basically
minus u
involving
squared.
a 1 minus u squared. Again, I got to deal with that coefficient.
Gotcha, okay.
But that's always easy to deal with.
Yeah.
I don't know. What do you think?
You can split it up.
So shave off a factor cosine of x.
Yeah.
Then apply your
The half angle or
I can't hear you.
Do it one more time.
Do what one more time?
Just split up the cosine 4 to the 4th
Well,
power.
you could just
Cosine
do
squared times cosine
1 plus 2x over 2, or do that, yeah.
Piece. Okay. Now just integrating 1 minus u squared, raise to the 2nd power. That's easy, isn't it?
Yeah.
Everybody?
Yeah.
Yes, sir.
Did you mean to write du or dx?
I definitely meant to write dx, thank you. Boy, I really didn't mind my P's and Q's still. Another mistake.
Dx.
Thank you.
Minus 10 points.
Man, my exam's going down to 0 points.
Is that secant of 4x or secant to the...
Secant to the 4th of x.
Okay.
You guys, I really can talk the way your author does. Think of this as tangent to the m of x times secant to the n of x. But I think when n is even, without going through any kind of memorization, I think if n is even, my life's pretty easy. Can you tell me why?
Because we have that memorized formula.
Which one? Oh, you mean the integral of secant of x?
Yes.
I think it's completely irrelevant with this. Sorry.
No, it's fine.
Secant of x 1 over
Because secant squared of x is the derivative tangent of x. And with what he just said, I think when the secant's being raised to an even power, who cares what's going on with tangent? I will shave off 2 such factors. Save 2 factors. Take the others, which are raised to an even power necessarily, and apply your Pythagorean identity. And I think that leaves me with a 1 plus tangent squared of x. Or shall I say, this leaves me with a tangent cubed of x plus tangent to the 5th of x times secant squared of x dx. Tell me what to do next. Clear and easy u sub, let a u be tangent of x. And I think at the end, all I'm really integrating is u to the 5th plus u to the 3rd, which is a piece of cake to anti-differentiate term by term, using the power rule for anti-differentiation. Again, you guys, if I'm not annoying you, can I not finish? I mean, once we get to the u sub, I think life's pretty easy, isn't it?
Well, when it's not pretty easy.
There's one question in
You
there
had to
that
ask.
just goes on forever.
So here I go. Well, maybe this isn't going that far yet. Give me another 2 or 3 minutes. So here's my m, here's my n. matter what n is, I think if m is odd, I think one thing that's very natural for me to do is shave off one factor of the tangent of x, if m is odd. Shave off one factor of secant of x, no matter what power is being raised to. Take everything else. Since tangent of x is raised to an odd power, when I shave one factor off, what's left over is an even power for the tangent of x. And as secant of x raised to, who cares what power? What remains are some powers of secant of x. I don't care how many. But in applying my Pythagorean identity again, but in the other direction, do you guys see what I'm doing? The tangent of x times the secant of x is merely the derivative of secant of x. I've rewritten everything solely in terms of secant of x. Now it's another quick and easy u sub. I think I'm integrating u to the fourth minus u squared. No exaggeration. Piece of cake.
So you just keep exploiting that relationship between tangent and secant?
I do. Now I admit, I looked at two special case scenarios where I've got this integral right here. Where in the first case scenario, n was odd. First case scenario, n was even. Second case scenario, m was odd, and I can play these games. But to me, I don't memorize that. I think of when n is even, I just naturally think of saving two such factors, rewriting everything in terms of the other function. In this case, that would be tangent. If m is odd, I can shave off a single tangent and a single secant factor of each, and make a u sub allowing u to be equal to secant of x. I can convert everything in terms of secants, because if that's odd, I shave one factor off, there's an even number left over, I can repeatedly use it, or I can use my Pythagorean identity to rewrite. What about this one? Is this the same or similar to example number 6?
Yes.
Of course it is. Okay, so this time around, I'm squaring this beast. Which means I'm squaring this beast. I can still commit to a u sub, u being the secant of x. It's just going to give me the integral of this. It's still just a Pauli expression. I'll explode everything up, distribute the u squared in, and be done with it. Now I can anti-differentiate term by term again. I think maybe the only tricky thing here with secants and tangents, what if it were the case that this particular m right here were even? That's odd. I think that's a bit more tricky. I think if m is even and it's odd, I guess something looks like this. And if that really is the case, there's not much I could do to make my life easy. But you have to confess, since this particular expression, the tangent of x is being raised to an even power, maybe I can think of it as secant squared of x repeatedly. And then use my Pythagorean identity. I misspoke, didn't I? I meant to rewrite a single secant factor. Did I make a mistake again? Man, what is wrong with me today? Look what I've written on the board with my line through it. What did I really mean? Yeah, here's a tangent squared. Here's a tangent squared. But those are equivalent to -1. Oh, well, that's one of them. One of the tangent squareds. Here's the other one. Oh, shoot, I missed a few, didn't I? I guess there's one here. There are 3 of them here. Now, if I blow everything up, it's going to give me this. You tell me if I'm walking too fast with my math B. I'll let that marinate. How's that looking so far? So, you guys humor me with this. Above my red squiggly line, how would you integrate that? How would you integrate that?
Would you multiply it by secant x, tangent x, over secant x?
close, close. Why not do this? Split this up into secant of x times secant squared. There's your u and your dv. Now we can use integration by parts. We get another expression involving an integral, for which if you apply your Pythagorean identity, you get another secant cubed. You can solve the equation. You saw me do this in class last time. Well, before the exam. What about the one involving secant to the fifth? Well, I did it in class 2 in front of all of you. I reduced it down to secant cubes, but we already know what that is equal to. Solve another equation. Unless you're getting a headache, then you can apply the reduction identity in the back of the book that you and I proved in class that allowed us to integrate secant to an odd power.
So, is there
Yes.
ever, like, so question number 4 up there, we could use reduction formulas in order to
You know, I
get
can.
that
It's
right.
just when it comes to sines and cosines, why bother since it's that easy?
Yeah.
I do think, however, with secants or cosecants for that matter, raised to an odd power, I think that's a lot of work. I
So-
have to repeatedly solve those equations.
You're going to get a different answer, too, if you do the reduction formula, right?
Yeah, but I promise you, the other answer, if you repeatedly apply your Pythagorean identities, you can
Yeah.
make it look just like this one. I see your point. I can see that. And that happens a lot. You're going to do it one way, the author does it a different way. You look at your answer saying, oh, I messed up. The answer in the back of the book involves something completely different. Well, not completely different, but the other co-function. And now you can bridge the gap, barring any errors, by repeatedly using your Pythagorean identities.
Okay.
That happens a lot. Or if you're using technology. A lot of times your technology would do it one way. More clunky with it, you would, with the use of it.
Okay.
So, cosecant and secant are the only ones with the reduction formula?
No.
Oh, no, I wouldn't say that at all. I mean, I've got reduction formulas involving sines, cosines, tangents, cotangents. I'm just saying, I don't think in this particular example, number 4, I would even look on the back of the book for a reduction formula identity, since it's just such an absolute piece of cake to do it by hand. I do think, David, that's a lot of work.
Yeah.
And I don't want to go through it. But there I might use my reduction. But I could. I could do it just like I did yesterday in class using my integration by parts formula. So bottom line, convert to secants to odd powers. A lot of work involved. You might want to use that reduction. David.
The reduction formulas make me very nervous in the sense that they're pretty complicated, and if every function has a reduction formula.
I hate to say every integral does, but I'm listening.
Well, like the sines, cosines, and all the tangents, and the secants, and the cosecants, and the cotangents, and there's a lot there. And, you know, we don't have a math brain, or I at least don't. And it's, well, when it comes to test time and we're get like tangent to the 15th of x and go for it, you're stuck looking at it, and you're up a bridge without a, or up a creek without a.
Yeah, but I being a mathematician the same way, I don't memorize his formulas. And so expect an exam situation that if I wanted to use one of those, I'd give it to you. I really would.
Okay.
Or a better test question would be this. Here's a reduction formula. I promise you it works. Prove to me that it works. That'd be, I think, it'd be a much better question.
Pretty easy to derive, too.
It'd be pretty easy to prove that it
Yeah.
works, just like I did in class with that one reduction identity. I proved it as well.
That was some of our homework from last night, too.
I hope there was. I
Yeah,
don't remember.
yeah, it was on there.
Sir, I'm sorry, I talked right over you.
So what would that be evaluated? So I completely, your explanation completely went over.
I give up. You know, at this point, I would use that one reduction identity you and I had in the back of the cover of the book that said, if I've got the integral of the secant, if I can spell it, I really can't, jeez, n of x dx. Here's an example where I probably would just come and use a reduction integral in the back of the text.
Okay, my terminology might be different. What's reduction?
Oh, sorry. Let me show you. Let me put it on the board, if I can find it. See, I'm being honest. I don't remember it. Because I never used it. You guys, if I turn to the back of the text, the inside cover, I see a mathematical statement. By the way, we proved this in class last time, but let me reiterate what it is. This is number 45. It says, if you got the secant to the n of x in the integrand's position, you can rewrite this in the following fashion. Secant n minus 2 of x. Tangent of x all over n minus 1, plus an integral of this fraction of the integral involving secant to this power. Sir, can you appreciate the fact that if I allow n to be 7, oh, I guess some garbage here. Who cares what the garbage is, because technically speaking, it's not an integral. But notice how the next integrand, I got secant to the 5th power of x, with respect to x. I reduce the order of the exponent from 7 down to 5. Now, for this integral involving secant to the 5th, I'll apply this reduction identity again, whittle this down to a secant cubed. Now, when it comes to secant cubed integral, I can apply this reduction identity again, reduce it down to an integral involving secant of x, which you would finally rewrite as. I said, the last integral involves secant of x, which you will finally rewrite as the natural log of the absolute value of secant of x plus, I feel so alone, tangent of x, thank you, plus c. Right? You would do that, wouldn't you?
Yes.
Good. Wow, I feel like I like a windstorm went through this topic of trigonometric integrals. I just don't think there's a lot here, if you don't mind me saying. I said if you don't mind me saying. Oh, you guys, I don't want to waste our time, so you know what I did? With these trigonometric integrals, life's a piece of cake. But just because I'm worried about wasting our time, I know I made some examples up. What I want to discuss next. I think this integral is interesting. In that, if I take my denominator and factor out a common factor of x, here's what's left over. Now personally, if in the integrand's position I see a sum or a difference of two squares, I naturally think of making a very new type of substitution. I refer to it as a trigonometric substitution. These trigonometric substitutions do the same thing every single time. They exploit your Pythagorean identities. But these trigonometric substitutions are very backwards. I am not going to come in and say, oh, let's make a new variable out of thin air and express this as some junk in the variable I already have. It's going to be quite the contrary. Instead, what I'm going to do is I'm going to allow x to be equal to something in terms of a new variable. That's why I'm saying it's a very backwards type of substitution relative to what you're used to so far. Now, in the integrand's position, if I have the sum of two squares, like these two, I naturally think of letting x be equal to the tangent of theta for this one very good reason. I get to take this two-termed expression and replace it with a one-termed expression using my Pythagorean identities. You guys, can I give myself more room? Here's my tangent of theta. I meant to have a factor of a in front. I'll close my pen. So listen to my choice of words. If I replace this x with this, don't I get a squared tangent squared of theta plus a squared? Now I get to pull my factor of a squared out. What's left over is tangent squared of theta plus 1. But another name for tangent squared of theta plus 1 is secant squared of theta. I get to replace a multi-termed expression with a single-termed expression. Let's give it a shot. In my example over here, a is 1. My life's easy with my first example. If you allow me to replace x with the tangent of theta, let's give it a shot. Does that give you this? Another name for x is this. Another name for x squared plus 1 is tangent squared plus 1, which is this. I want a yes or no answer. Are you happy?
Why is it plus 1?
I have no idea. It's tangent squared of theta plus 1.
Yeah.
I didn't mean that mistake, but I did mean another one. I still think I'm wrong. not as quick as replacing dx with d theta, is it? Alright, I think this is a serious error. I've got to commit to the substitution, and now let's see when I relate dx to d theta, what do I get? Very nice. Okay, I'll fix my mistake. I guess that means I've got an extra factor of secant squared in the integrand position. Excuse me. And now with a tad bit of cancellation, I'm merely left with the integral of my cotangent of theta with respect to theta. David,
Why did you choose tangent to be your x and not any other property, just for that particular reason?
what a good question. You know, if I allow x to be secant, I get secant squared of theta plus 1, and with one of your Pythagorean identities, I don't see a secant squared of theta plus 1. I only see a secant squared of theta minus 1. That's why I'm saying, when I see a sum of two squares, I naturally think of the tangent substitution. Even a sine function or cosine is not going to give me something for which I can replace those two terms with a single term using one of my Pythagorean identities. You guys humor me. Are you able to value this integral? What do you get? Well, Ln of. So I think you do. I agree with that because I think what you and I have sitting in front of me is nothing more than this. Which is equal to this.
Can you do that earlier? Is it cotangent is 1 over tangent theta, and then since you had x equal to tangent theta, can you going to skip that and just say, okay, at that point it's 1 over x?
You know, it's not that smooth. It's really because I got this cancellation once I evoked this trigonometric substitution that it really works.
Go back to the x if you did that.
Well, because right here you get 1 over tangent theta d theta, right?
Yes, a sloppy theta, sorry.
Why can't you convert back right there? Can you explain why it's more difficult?
Convert back to 1.
To x.
Because dx isn't equal to d theta.
Because, yeah, dx has to be replaced with x.
Oh.
I think that would be quite a bit of a change, a switch. You guys, everybody, I know I skipped a step. I allowed you to be sine of theta. Yes or no? Is that okay? If it is, listen to great. I think that leaves me with the natural log of the absolute value of u plus c, or the natural log of the absolute value of, what was it, tangent? I lost it. I misspoke. I meant secant, or sine of theta. Oh, that's so nasty. I didn't remember all my cotangents. I'd like to rewrite it in terms of secants. Can I do that?
Sure.
Sure, piece of cake. I said, sure, piece of cake. Negative natural log. Absolute value. Cosecant theta. Very nice. I agree. Now is everybody happy? Finished?
How do you
What do you mean
force
done?
that?
Okay, what?
How do you force that?
It's 1 over sine.
Oh,
So far, so good?
Well, no,
No,
'cause you have to put the negative.
Look, I reciprocated. Let me undo the reciprocation. And now let me put the negative sign out. David, I'm showing all my steps.
yeah.
And now let me rewrite the inside.
So why is that better than just having natural line?
Bradley, in this example, it doesn't make any difference. I think it'd be easier to stop here because I'm
Yeah.
not finished. I'm just saying if I really wanted to, I can express the integral involving cotangent in terms of cosecants because, yet again, another intimate relationship with those two functions. That's what I'm suggesting.
Just showing off.
By the way, have I answered the question? Why haven't I answered the question? Because it's not in terms of x. Thank you. I got a back substitute.
On the last two lines right here, where did the negative come from?
I made it up out of thin air. I was suggesting, if I really wanted to, I can reciprocate this and then undo the reciprocation. Pull the negative sign out and just stay with cosecants. If I really wanted to. You guys, I don't need to be annoying you. Look, watch me. Eraser. I didn't have to. I'm just saying I could have. So everybody, whether you're down there, up here, it doesn't make any difference unless you and I back substitute. And another name for sine of theta clearly from this is, clearly is. See, I think it's not very clear at all. But I do think, if I were to take theta and embed it in a right triangle, to say that that theta angle is tangent is equal to x simply means a ratio of this side to this side is x to y. Which, by the way, means a hypotenuse has length √1 plus x squared. Which, by the way, means I can replace the sine of theta with nothing more than what?
Inverse tangent of
Say it
x.
again. I was hoping you wouldn't go that far. So x over square root of stuff. Do you guys agree? Now I back substituted and rewrote in terms of x's. You're so excited. Get some rope to tie you down. Because you're bouncing all over the place. How about something like this?
No, was that absolute value necessary?
Yeah. I don't know if x is positive or negative. No, I cheated. I didn't put it downstairs because the output of squirting operation is always going to be
So would it be wrong to just do the natural log of the inverse tan, or, oh, because you'd have to sub that in. Never mind. I see what you're doing.
It's not gonna be wrong. I mean,
I see
right
what you're
inverse
doing,
tangent of
yeah.
x, I see it, but the sign of the inverse tangent of x looks so clunky, and you're
Yeah.
gonna yell at me.
Yeah.
But I have my trick students get so much practice taking that the next step. It was another big trig issue. You said you took trig here.
Yes, I took trig here.
Yeah, okay, that's all I want to know.
We did inverses in trig though.
But she didn't write in terms of algebraic expressions.
Not really, no.
Anyway, now you see why.
Yeah.
It's important. How about something like this? How about the integral of x cubed plus 1 over root stuff? You guys, I think this is different. I think here's a second case scenario where I'm left with the difference of these two squares. Now let me impress upon you how nice this is. If I come in, whenever I have an expression like this in the integrand position, and allow x to be equal to a times the sine of theta, close my pen, I'm not going to write, I just want to naturally talk about this. This becomes an a squared minus a squared, sine squared of theta. But now when you factor out, did you get all that down? Okay. Now when you factor out the a squared, you're left with a 1 minus sine squared of theta, which you can rewrite as cosine of theta. Well, cosine squared of theta, single term. Let's give it a shot. Oh, I don't want to. Can I separate this? In separating, that gives you the sum of these two intervals. Now, in committing to my particular trig stuff, with the first integral, this gives me the integral of, let's talk downstairs. 5 minus x squared has another name of 5 minus 5 sine squared of theta. But that's the same as this. Oh, it's okay, I can still do it. We'll let x represent the square root of 5 times the sine of theta. Make it legal.